Finally, we made two chemical reactions, right? Isn't that what chemistry is all about? Doing reactions? No, we are not going to make explosives, but it's still going to be fun. Yeah. Okay. We use symbols to represent atoms, molecules, compounds. So there has to be a way to represent reactions, and that is the chemical equation. The chemical equation will show you what are the identities of all the molecules involved in there, the quantities. So how do we write a chemical equation? Here you have an example, CH4 molecule plus 2 oxygens yields, that's an arrow, carbon dioxide plus H2O. Whatever you begin with is called a reactant. Whatever you end up is a product. The reactants are always on the left, the products on the right. They're separated by an arrow that, like I said, means yields. The reactants are represented, are joined together by a plus sign, the same thing with the coefficients, with the product, sorry. And then you have coefficients, then you have many. You have 2 oxygens, you have 2 waters. Okay? So writing a chemical equation is very easy. This pretty much tells you the same thing. What is a reactant? What is the product? Use plus signs to separate reactants, to separate the products, an arrow between reactants and products, coefficients tell you how many molecules. This is exactly what I just explained. When you're thinking about coefficients, watch out because this is a common problem. The smallest possible whole number coefficients. Because you can write many different ratios, but like, look at this example. This is the molecule we did in here, and you say, okay, this is my oxygen, this is the methane. So I could say in theory, if I just count them, I have 3 methanes plus 1, 2, 3, 4, 5, 6 oxygens that produce this carbon dioxide. How many? 1, 2, 3. 3 carbon dioxides. And how many waters? 1, 2, 3, 4, 5, 6. Okay, this is a chemical reaction, but the coefficients are not the smallest possible numbers. Now, if you divide everything by 3, then let me just write it here because there's no room. So CH4 plus 2 oxygens divided by 3. That's carbon, gives me carbon dioxide plus 2 water molecules. Okay, that's exactly the same thing that we had in here. Okay, this one is correct, this one is not, because even though that is the correct ratio, it's not the smallest. And be very, very careful with that. Okay? Depending on the instructor, you may get partial credit, you may not get no credit at all if you don't use the smallest whole number ratio. The chemical equation that I gave you before was balanced because it has the same number of whole atoms. Let me write again, CH4 plus 2 oxygens, carbon dioxide plus 2 waters. And you're saying, okay, how many carbons do I have in the reactants? 1 carbon, 1 carbon. Okay. 4 hydrogens, 2 times 2, 4 hydrogens. Good. 2 times 2, 4 oxygens, 2 plus 2, 4 oxygens. You didn't create, destroy, lose any atoms. So it's balanced. You have the same number of atoms on the reactant and the product side. Okay? Just keep in mind whenever you have a molecule, that the number of molecules times the number of atoms in the molecule, that gives you a total number. And sometimes you have oxygen here to 2 different places, you have to add them. You say, I have one that has 2 oxygens, that's the carbon dioxide, plus I have 2 molecules that has 1 oxygen, so that's how I come up with 4 oxygens. It's just very simple bookkeeping. Okay, this is actually the same thing if it appears in more than one molecule, make sure that you don't miss any. So this one, like I say, is balanced. You can just look at the atoms from each one, no problem. What if I write this other equation? Water breaks down to hydrogen and oxygen. It's not balanced. How do I know that? Because you say I have two hydrogens on the reactants, two hydrogens on the product. Yeah, that's fine. One oxygen, two oxygens. I don't know if you can see, but this is not balanced. So what do? You have to balance. The oxygen is not balanced. Question is, how do I do that? Now, keep in mind, you cannot change the coefficients randomly. Okay, let me put it this way: do not change the subscript. Never. I have the students. Let me go back to the formula that was going to balance. And I had actually in an exam student, this is a real story, who changed H2O to H2O2. H2 plus O2. Now it's balanced. But this is not the question I gave him. This one had water, this one had hydrogen peroxide. You do not change the molecules. You do not change the subscripts because that changes the molecule. What you're going to do is change the coefficients in such a way, and only when needed, that you end up balancing the equation. So in this particular case, we said that we didn't have enough oxygen, so we are going to multiply the coefficient for water times 2, because now the equation will be balanced. So pretty much what we did in the essay. We're going to do two words. Okay, so now we have enough hydrogens in here. That's H2, sorry, O2 hydrogen. Now you have two oxygens and two oxygens, but now the hydrogen that was balanced is not anymore, because I have 4 hydrogens in here and only 2. That happens a lot. Okay, don't freak out. Many times when you're balancing one atom, it unbalances another one. That's okay. It happens. Now we'll worry and balance the other one. So all you have to do is put 2 hydrogens in there. Change the coefficient from the hydrogen. Now you have 4 hydrogens in the reactants, 4 in the products, 2 oxygens, 2. That's balance. It usually doesn't take more than 1 or 2, very, very rarely 3 changes. Okay? Now, I can give you some advice. Whenever you're balancing equations, always leave the pure elements for last. Okay? That's the last ones that you want to balance. It just saves you steps. Okay? If I change the number of moles of molecule, you saw that it unbalances another one. But when I change only hydrogen or change only oxygen, it doesn't change the other one. It doesn't unbalance the other one. So I try to just leave pure elements for the last. You don't have to do that, but if you don't, you're going to have more steps. It takes a little bit longer. The more steps, the higher the chance of making a mistake. Okay? But it doesn't matter if it takes you 4 steps instead of 2, because at the end, you're going to double check and make sure it's balanced. So if it takes 50 seconds longer, who cares? It's just, I always try to do things the easiest way, okay? And that has helped me tremendously with big molecules. Sometimes you find out yourself using fractions or decimals. You could have put a 3.5 in there too. Why? Because you have 2 carbons, 6 hydrogens, 3 times 2, 6 hydrogens. How many oxygens I have 3 plus 4, 7, but this is O2. So the only way I can balance it is to put 7 halves, or I could have said 3.5 oxygens. Now, we said that we have to use whole numbers. So that, even though it's balanced, is not correct. If I write everything times 2, then I get all whole numbers. So please do not ever give the answer with a fraction or with a decimal. If you need to multiply, go ahead. Just remember, you don't multiply only one, you have to multiply all of them. That's easy. Also, when you write a chemical equation, you're supposed to, at least that's what the UPAC says, put the physical state. After every molecule, you put a G if it's gas, an L if it's a liquid, S if it's a solid, AQ if it's an aqueous solution. So that is a proper equation. That's what the UPAC says. Most people say, forget it. It's time consuming, it's a pain. In fact, there is one time when you're going to have to do it, and you don't have a choice. But believe me, when you finish that particular worksheet, you'll be so happy. But I'm not going to tell you not to put the symbols. I'm just going to say, check with your instructor. Most instructors will say, there is no need. Everybody knows sodium is solid. Everybody knows water is liquid. You don't have to put it. Only put it whenever it's absolutely necessary. You're going to see sometimes, like, maybe I'm using steam, gaseous water. Make sure you indicate, because most people who read H2O are thinking of a liquid. So if it's unusual, by all means, put it. Like I said, when we get into molecular ionic net ionic equations, it's crucial that you put the state of the matter. The rest of the time, up to your instructor. I usually tell my students, don't worry about it. But some instructors may say that you have access to do that, so you don't want to lose credit because of that. Okay? Sometimes on top of the arrow, you can indicate special conditions, like you're doing at a certain temperature. This triangle means that you're heating. Calcium carbonate can sit in a bowl in the cabinet for years. But the moment you heat it, it produces carbon dioxide and carbon dioxide. So since you need heat, we indicate. Many times we are going to, any extra information we want to give it, we put it on top of the arrow. With molecular equations, no big deal, but ionic reactions, there's 3 different ways you can write them. Okay, because usually they are in aqueous media, so you can write them at different levels of detail. Do you want to give every little bit of information? Do you want to make it simple? So there's 3 different types of equations you can write. The molecular equation, you write the whole formula. Okay? It doesn't show you the ions, you just know the ionic. But you must include calcium chloride is an aqueous solution, silver nitrate is an aqueous solution, calcium nitrate is an aqueous solution, silver chloride is solid. How do you know that? We are going to cover that a little bit later, okay? You will have a solubility table that will tell you if a particular ionic compound is soluble in water or not. Do not try to guess. Do not try to remember what happened before. Because you're going to have a table. Look it up. Anything you remember or guess can be right, can be wrong. If you look it up in the table, it's always right. Okay? But again, the molecular equation, you write the formulas. Let me just put in there. Write formulas. So it doesn't tell you what ions are formed, but it's a very easy way to see the reaction. And remember to put the states of the matter. In fact, I take credit off if you don't put the states of the matter in this case, because when we move to the next one, we're going to separate the ions if it's an aqueous solution. That means we're going to break down this molecule and this one, but we are not going to break this one because it's solid. That means it's insoluble. Now, if you don't put the state of the matter and then you give me the next one, I'm going to ask you, and how do you come up with that? So this is the one case when you have to write the states of the matter, in my opinion. This is not just because the UPAC says it, it's because you need it to do the next one. Because ionic compounds usually dissolve in water and dissociate, but not always. So calcium chloride dissolves and the ions separate, silver nitrate dissolves and separates, calcium nitrate dissolves, but silver chloride does not dissolve, so it does not dissociate. So when we write the equation, we write the ions for those that dissociate. There's one calcium, two chlorides, two silvers, two nitrates. This is supposed to say aqueous. I don't know why. Sometimes when I copy things, it doesn't work. Calcium nitrate breaks down, but silver chloride did not break down, and you have to indicate it's solid. They all are aqueous solutions, except for the silver chloride, because it shows all of the ions that are formed. That is a complete ionic equation. Now you can say, yeah, but calcium ion appears on both sides, and the nitrate appears on both sides. Can we just cancel it out? Yeah. You can simplify the equation by removing those that appear on both sides. We call them spectator ions because they don't do anything. I mean, don't get me wrong. They're there to balance the charges. They're there because if you have a calcium ion, it has to be a something calcium. Okay? It's calcium chloride, it's not calcium carbonate. But they don't participate in the reaction. That's what I'm trying to say. So you can eliminate the spectator ions, and what you come up with is a net ionic equation. Here you have the total ionic equation. We eliminate calcium, we eliminate nitrate. There you have the net ionic equation. The net ionic equation is easier to see, easy to understand, but gives you less details. I don't know what silver salt I had. I don't know what chloride salt I had. I don't know what else was in the reaction. But notice in the problems or in the exam, are they asking me for the molecular? Write the whole formulas. Total ionic, write all of the ions that are formed. I've been putting comments, so you write all ions. Obviously, the one that's solid does not dissociate. So there's no ions for an insoluble. And remember to put the states of the matter. Okay, that's the complete or total ionic equation. Both names are used. In this case, you put only the participating ions. You don't put the spectator ions, and again, you still put the states of the matter. This is the only time when I insist to write the states of the matter, when you're writing molecular, total, and net ionic equations. The rest of the time, you're free. Okay? The key to go from molecular to the other ones is knowing when something is not soluble, and that's what you're going to get from the solubility table. That will be given to you. You don't, well, I shouldn't say that. I know at least one person who teaches chemistry who expects the students to memorize the solubility table. I don't. You may want to check with your instructor and make sure, but most instructors will say, no, I can't give you that. That's trivia. Okay, so once again, practice makes perfect. I have a long worksheet where I think it's 10 different equations, and for each one, I ask you to write the ionic, molecular, net ionic equations. You want to do that? Very simple. All you have to do is go to the video description, go to Wyson, make an appointment, and I provide you with that worksheet so you get to practice a lot. Especially, it's good to practice whenever something is not going to be graded. I will correct anything you do. I will tell you if you're right or wrong, but it doesn't affect your grade. So you see what mistakes you make, and then when you're doing something for your instructor or you're taking an exam, you know not to make those mistakes, and you get a better grade. Isn't that good?